Clinker Factor, the cement industry podcast.
Welcome to the Clinker Factor, a podcast from WCA which looks at the cement industry's response to climate change around the world and other topics of interest. I'm Ian Riley, CEO of WCA and your host on the Clinker Factor. Before we get started, I want to draw your attention to the 2023 WCA Annual Conference, which will be held on October the 24th and 25th at the Emirates Towers in Dubai. And we still have a few exhibitor slots available. So we'll put a link to the registration website in the episode notes. Today I'm talking to Gianluca Ambrosetti, who's the CEO of Synhelion. Gianluca, welcome. Can we start by asking you to introduce yourself and how you came to found Synhelion?
Well, thank you very much for having me, and it's a pleasure, to try to show you a bit our take on synthetic fuels and also how we can help to decarbonize cement manufacturing. So I'm Gianluca Ambrosetti. I'm the co-CEO and co-founder of Synhelion. Synhelion is a Swiss company, is a spin-off of the Swiss Federal Institute of Technology. It was founded in 2016 to bring to the market technologies for the production of renewable fuels. So fuels that basically have the same features as today's fuels, but made in a renewable way so that they have like a minimal impact on the environment. And this stems from decade-long research that was done at ETH Zurich by Professor Aldo Steinfeld. And our mission was to bridge this into the market. And we started in 2016. In the meantime, the company has grown. There is something important about our take on renewable fuels. There are several ways to do renewable fuels, but our take has something particular. And this particularity is that we use high temperature solar heat. So we use typically a set of mirrors to concentrate the solar radiation onto what we call a solar receiver, where we attain very high temperatures, above 1,000 degrees and up to 1,500 degrees. With these high temperatures, we derive what we call thermochemical processes to the production first of synthesis gas, a mixture of hydrogen and carbon monoxide, which then can be transformed into liquid fuels via traditional gas-to-liquid processes such as Fischer-Tropsch and methanol. Now, however, stick to the heat part. This is very important because this is also what brings me to another declination, or let's say another line of developments that we are following, which is the one of solar cement. So as we have cheap high temperature heat, what we can also do is we can also derive cement pyroprocessing, substituting the need to burn other fuels in the kiln and the precalciners. And this is what we do together with Cemex in the solar cement lab. There is, however, a nice icing on the cake. And, to do fuels, we will have the energy, we have heat, but we also need chemical inputs. When you burn a fuel, hydrocarbon, you will have as a product CO2 and water vapor. If I want to produce my synthetic fuel, we'll need to take these products and reverse the combustion process. This means that I will need some water and I will need some CO2. From where do I get the CO2? Well, there are several ways to source this, but one for sure is to try to get it at the point of emission. And here there is an interesting, very special part in cement manufacturing. Even if you substitute the whole pyroprocessing, say, fuel demand, you still will remain with 2/3 of CO2 emissions coming from the calcination of limestone. Those are inherent CO2 emissions that come from the process that cannot be substituted, if not, let's say, sort of more advanced formulations. But let's say in a standard Portland clinker, they will remain. So they are a perfect feedstock that we can take for producing our fuels. So we'll have a solar cement plant that is decarbonized by the solar heat provided by our technology. And at the same time, we have a concentrated stream of calcination CO2 that we can use nearby or a bit further away in a fuel synthesis plant. So we have like this double sync.
Yeah, so I think that kind of circularity is very interesting, and people are finding more opportunities for that kind of thing. Could I just start there by asking you something a bit more basic about the technology? Well, we organized a field trip at our last conference in Dubai, October last year, to a direct solar plant there. And I think that's the same thing that you're talking about, isn't it, in terms of the concentrated heat? Is there a relationship between PV solar and solar heat? Are they completely different technologies? I guess they both rely on the sun. So in some sense, they both work in the same places, but the technology is quite different. Is that right?
There is a difference in the sense that concentrated solar and the facility that you have seen is actually another declination of also what we do. I mean, most of these systems with this large array of mirrors concentrating on top of a tower are used to produce high temperature that is then used to drive steam cycle for the production of electricity. We do it different. We do our fuels or solar cement, but the concept remains the same. PV is, in a certain sense, different because it goes directly to electricity. Of course, you can also combine PV with a heating system and you come to heat. This is tendentially less efficient in the chain. So you need to do it well to come to cost of heat that are meaningful. But nevertheless, there are some particular case where this approach makes sense. But let's say the big advantage of concentration, direct conversion of the concentrated solar irradiation in high temperature heat is the efficiency of the chain.
So generally speaking, we don't want to be moving between heat and electricity backwards and forwards. We always lose some efficiency. So if we want heat, then let's start with heat. So in the cement application, can you tell us a little bit about how that works? Is the heat only being applied in the pre-calciner, or is it applied in the kiln as well? What's the concept there?
We do have, with our technology, let's say, unique high temperature capabilities. We can go up to 1500 degrees. This is enough to drive the whole pyroprocessing stage, which in a traditional architecture would mean, of course, the pre-calciners, but also as well as the kiln where you do the clinkerization. Now, we of course look at optimizations. Of course, the biggest energy demand comes with the calcination phase. So you may, in some case, consider to do only that. However, we are also looking at the entire process, and most of the experiments that we are doing is including these, exactly because we have these high temperature capabilities. Another thing to say is that we are also thinking at totally different architectures. I mean, like today's pyroprocessing stage is highly optimized for what it does and the way it works. With a different approach as the one that we are using, things may change. And it's important to mention a bit, I may give you a bit more context on how it works, just to put some of these comments in perspective. So what we have is where we concentrate the solar irradiation, we have a solar receiver. In the solar receiver, we heat a heat carrier, what we call in solar energy jargon, heat transfer fluid. This is a gas, and it happens to be a mixture of water vapor and carbon dioxide. This then flows to the process to be heated. So it can be flown directly in the kiln or in the pre-calciner. It will mix with the products, the CO2 produced by the calcination process. This is, however, not a problem because I can then take out a part of it, and being water vapor and CO2, with some energy penalty, I can condense out the water vapor and land with the pure CO2. So it's a nice system where I don't have too many heat exchangers. Is everything fairly, let's say, integrated, and I can I can extract the concentrated CO2. It's also important to mention another component to the system, which I didn't mention so far, is the thermal energy storage. This is a very, very important part because I guess many of you may be wondering, okay, nice, I can have my whole pyroprocessing working with sun, but what happens at night? The beauty of this process of having a receiver heating this fluid is what in solar parlance you call it an indirectly heated process, is that during the daytime, a part of the heat goes to the process itself, and the bigger part goes to the thermal energy storage. It's a big vessel filled with refractory bricks, which you heat up. So that during the nighttime, you basically can drive the process with the heat that you have stored in the thermal energy storage. And this allows you to work 24/7. is really a cornerstone of working with heat. We mentioned before electricity. The efficiency chain is for sure one of the things that can be problematic, but the biggest one is continuous production, because if you want to be grid independent, and this at a certain point we'll need, like we have a scarcity of renewable electricity from the grid. So if you want to do a large electricity intense project, nowadays you will need to tend to make it grid independent. Yeah. And you need storage, and storage means batteries, and batteries are expensive, 10, 20 times more than heat storage. And this is while, we always put a bit an accent on this thermal energy storage guy that allows to run this process.
What difference does it make in terms of your weather conditions? We were talking about Dubai earlier, and obviously they get a lot of very concentrated sunshine. Does the economics of solar power and solar heat vary a great deal with the location in the world?
This is a very good question, and the short answer is yes, it depends a lot. I mean, I'm here in Zurich. We may have like the reference figure for concentrated solar is called the direct normal irradiance. It's the solar irradiation that comes from the solar disk and a tiny portion around it. So we may have a DNI of 1,100 kilowatt per square meter per year in Zurich. If I go to Spain, the first place where things start to make sense, you will be around 2,000, 2,200 kilowatt hours per square meter. If you go to the best place in the world, in the Atacama Desert, you may have 3,700 kilowatt hours per square meter. So basically, at the end of the day, with the same plant, the same capex, you produce 3 times as much. Yeah, you can do your math. I mean, at the end of the day, the cost of heat is in solar is basically the investment. Is the levelized cost of heat is dominated by the investment and what you produce. So the operating costs are, let's say a tinier fraction of this. So if you produce 3 times as much, roughly your cost will be 3 times less for the same amount of heat. So it does matter significantly.
Yeah, no, big difference. Can you tell us a little bit about where Synhelion is in terms of applying the technology, either in fuels or in cement?
Sure. So, I mean, for the fuels, we are basically now building our first A to Z industrial scale plant in Germany. Germany is, as I just said, is not an ideal location for production, but is a very good location for debugging the technology. So bringing everything together, those are very complex plants. And we then plan a successor, the first, let's say, commercial plant around 25, 26 to be online. So there we have, a fairly defined timeline. Solar cement is also coming along very quickly. We are having a very good campaign this year in Spain. We are testing some new setups and some new configuration at the facility on the outskirts of Madrid. And we plan next year's together with Cemex, this is of course a close collaboration with Cemex. We plan to further develop the technology in a few declinations, so that not in too long we will be able to have, like, let's say, the first demo plant. It will take a few years, but we are trying also there, to come to a fairly swift bridging between, like, say, early experiment and what it is an industrial reality.
And do you have a clear view of what that initial plant might look like? Will it just look at the preheater, or will it look at the precalcine, or look at the kiln as well?
I mean, as I said, we look at both. I mean, this at the end is a techno-economic optimization that you will need to do once you have an architecture that is defined and the plant size. We know that the low-hanging fruit is in the calcination. However, it may turn out that even going to the maximum temperatures and doing the full process, which of course entails some additional constraints and complexities, may be beneficial because you can get rid of basically most of the traditional heat sources. So we are evaluating. We do believe that there is a lot of potential in the entire integrated system, but calcination alone is also a very interesting space because, I say, it's the low-hanging fruit, is the biggest part of the heat demand.
And I guess almost all of the CO2 from limestone is coming up in the precalciner. So if you wanted to do carbon capture, then you would get it all. I mean, in a decarbonized heating system, then you would get it all at the precalciner.
Exactly. So this is where you would get most of it. So this is also why, of course, calcination only is something that we are looking at. Of course, we are looking at a pathway, both, like, let's say, both scenarios.
Are there ways of optimizing the plant design for using solar heat as opposed to traditional fossil fuels or combustible fuels? Is that something you've looked at in terms of how the configuration of the cement plant might change if you were building a new one rather than retrofitting? If you were starting with a greenfield, would it be would we not recognize it as a cement plant? Would it look completely different?
This is a very good point, and I touched it a bit previously. This is, of course, something that we are looking very much at. This is a central part of the development. Since the beginning, Davide Zampini always said, we need to be careful of not being caught into thinking, in trying to tweaking around the design that has been optimized for something else. We need to think, like, start from a clean sheet of paper. And this we are doing in several ways. We are looking at configurations that go very, very far from what you have seen up to now, down to configurations that are very similar. There are some similarities that allow you also that, the system seems to work also fairly well with a traditional architecture. However, we're also trying to exploit everything that we can out of it, to try to really have like the best synergy combination so that we can squeeze out the maximum. And there sometimes it goes into configurations that are fairly removed for what you have seen so far.
I think in talking to some of the carbon capture guys, they were saying if you use an oxy-fuel system that you can wind up with essentially a slimmer kiln because you don't have to carry all the air around. Presumably you might have the same benefits with the solar heating as well.
Yeah, this is actually a very good point. And it's quite ironic that we use as heat transfer fluid, the same as the product of oxy-fuel combustion. And this is important. I don't know all the reasons why you can make a slimmer kiln in the oxy-fuel case, but what I do know is that the oxy-fuel case will have a flame, will have like a gas that radiates much more strongly because the heating from the gas comes from the radiation of CO2 and water vapor of the combustion product. The same thing happens in our case. We use these gases; those are radiative gases. I didn't say it before. It's also a bit more technical, but very central to all our technologies, the use of these radiative gases, which are also, ironically enough, greenhouse gases, and they're very strong absorption and emission bands in the infrared spectrum. So you have for the same mass flow of, let's say, a molar flow of heated gas, a stronger radiative contribution. So you can resize the components, and this is also something that we are doing, trying to optimize this.
So just leaving technology for a moment and looking at the commercial side of things, do you have a feel for what the fuel costs would be relative to current practices of coal and alternative fuels? Do you have a sort of target for a solar plant? And I guess based on what you said earlier, it will make a lot of difference as to where that is.
So depends here if we're now talking about the cost of fuels, of synthetic fuels produced with our technology, or let's say the cost of heat, or let's say an integrated plant. So for the cost of fuel, we have very clear targets and ideas and analysis. Of course, this is something that, this is the cost of the product. And our long-term target with fuel is to have production costs of around €1, $1, 1 Swiss franc per liter. This is production cost, is not sales cost, so it will, the price at the end will be slightly higher. There will be margins embedded in it, but also this figure is not fully set in stone. But what is very central about it is that it is comparable to today's fossil fuels price. It will be more expensive. Some people claim that they can do it cheaper than fossil fuels. We believe that with low fossil fuels price, this is not the case, and we should also get used to this idea. But it's also not 20, 30 times more expensive because it would make no impact. Nobody would adopt it. Society can cope with a factor 3, perhaps 4, but cannot cope with a factor 20. Society and the eco. So far for the fuel. So for the cost for cement plants and the cost of cement, as we are still a bit away, from defining a full architecture and, like a full plant, we cannot give yet a clear figure. But we know that, that we estimated early on in the early economic analysis that a greenfield plant built in the right location with, let's say, the right boundary condition will cost some 10-20% more than a traditional greenfield plant. And from there comes the cost, the related cost of green clinker.
So the operating cost of the plant would be lower, would it? Because you don't have to buy the fuel.
Yes. Exactly. But you have you have a higher investments at the beginning, so
Right.
at the end, it's the levelized cost of heat to the process that defines it.
So you go from essentially purchasing your heat to making it yourself, and therefore the cost being the capital cost, the maintenance of the plant.
And of course the commodity and of course the raw material that you need to buy in, and all the other.
So what other raw materials will you need to buy in just for the operation of the solar heat? You mentioned, water and CO2, so that sounds something that will come from the process anyway. Are there other materials that have to be bought in?
For the fuels and let's say the heat part, not. I mean, I was more referring, in the cement plant, you will have, of course, the quarry and everything. And if it is your own, and also there, I don't know actually everything that comes in, this CEMEX knows. I'm not a cement expert. But let's say on the fuels and heat side, let's say on the heat side, there is basically no demand besides spare parts and, some refractory materials to be changed here and there. But let's say it's more like a standard plant maintenance as it would be like the kiln maintenance. For the fuels, of course, you need a feedstock, and if you get out, if you have CO2 coming from the cement plant, you have the CO2. You will need to have water, enough water, to do the process. This is it's also an important part. If you are in a very dry area where you often are, where you have very strong solar irradiation, you will need to take care of that potentially desalination and boarding it.
Yeah, well, it sounds a very interesting possibility, especially for cement producers in countries that have a lot of sun. Perhaps sitting here in London, it seems slightly less likely in the UK. So Gianluca, thank you very much for talking to me today. It's been most interesting to learn about your company and the technology behind it. I wish you all the very best for the future.
Thank you very much. It was a pleasure. And yeah.
Thank you.
Thank you very much.
Thanks for listening to the Clinker Factor podcast today. If you've enjoyed it, do subscribe and please recommend us to friends and colleagues and anyone else who you think would be interested in what's happening in the cement and concrete industry around the world. WCA is a not-for-profit company, and please visit our website to see the services that we offer